So we are on page 329, question 6. I'm going to give you a chance to read it and see if you can make a start. As I said yesterday, these questions are really hard. So if you are finding it hard, it's not that you are silly and missing something that everyone else is getting, it's because they are. Knowing where to start is really tricky with this one. I need dH by dt, and we've done these sorts of rates of change questions. So just do me a couple of things. Can you write for me what dV by dt is? That's the rate of change of volume. That's how the volume is changing every second. And there's a couple of things you need to consider, because you've got water coming in and water going out. And can you also write me a formula for the volume of the cylinder, of the cuboid, which will involve h, which is the height. So you could differentiate that to give me dV by dH. And I'm sort of hoping you could then combine those two things to make dH by dt. So dV by dt, that's the rate of change of volume, and there's two things happening. Water's going in and water's flowing out, so that's going to be something take away something. And the volume of the cuboid, which is length times width times height, but they give us some information which means that that's a little bit simplified, and differentiating that is very simple. And then combining those two things to make dH by dt, and then hopefully turning that into the formula that we've got on the board. So the volume is 600h. Length times width is the area of the base, which is 600. 6,000. Thank you. And multiplied by the height, which they are calling h. The change of volume is constant water flow in, 12,000 centimetre cubes per minute. Sorry, not per second, per minute. But variable coming out. It's a function of the height. I guess that's because higher it is, perhaps the faster it's going to flow out. So that's dV by dt. I want dH by dt. So I need something with a DH on the top and something with a DT on the bottom. Haven't got anything with a DH on the top. George, how can I address that problem? So if I flip dV by dH to get DH by dV, I've got something with dt on the bottom, so I'm hoping it's got a dV on the top to cancel out that one, and bingo, it has. So that's going to become 1 over 6,000 times or and hopefully you can see what they did then. They divided that fraction, so it wasn't the whole equation, just that fraction, by 100 and multiplied by 60. Now, because you don't need to beat yourself up if you don't see how that, if you wouldn't have seen how that got there, because that's 3 marks of an 8-mark question. Because they're giving you this, you can still go on and do the next bit. So the next bit is what we're doing at the moment. It's the separating the variables thing. I'm going to leave the... Tell you what, no, I did this the other day with the other group. I'm actually going to move... I've tried to decide what to do with the 60, whether to leave it there. This needs to come across. I can't just move the 5h because I'm only multiplying or dividing both sides. So that's got to come across as one thing. Yeah, I think I'm going to leave it where it is, the 60 where it is. So I'm going to say, right, I've got 60 over 120 minus 5h dh. And on the other side, I've just got... Remember, when I divide both sides by that, I'm not left with nothing on there, I'm left with 1 on there. Now 120 minus 5h, if you 1 over 120 minus 5h, if you integrate it, gives you ln of 120 minus 5h. It's a linear function divided by minus 5. What do you get when you differentiate the bracket? So 60 over that will give me 60 ln. So just see if you can simplify. Yes, Pat?
Would it be an idea to divide it by 5?
You certainly could at that point. That would be very sensible, wouldn't it? Yeah, as long as you divide everything by 5.
Does that mean the one right as well?
That'd make it a bit easier, wouldn't it? So that's... I like that. I like that a lot. It's a bit nicer, isn't it? So this would become 12 ln 24 minus h, all divided by minus 1, which is what you get when you differentiate that denominator. I've got a couple of options at this point. I'm okay to substitute my boundary condition in here because it doesn't give me a negative in the ln. If I want to e both sides as an alternative to that, I've got to sort out that minus 12. I need to have the ln statement on its own. So if I want to e both sides, I'm going to rewrite it like this. I'm going to divide both sides by minus 12, and here's how I'm going to write that. Pick a letter. You see what I've done there? Minus 1/12 times c is still another constant. I know actually the other day I did it where I just kept it at c. I think actually it's probably a good idea to change the letter just to indicate that you realise you should have done that. And then I can e both sides.
Why is it necessary to read both sides?
In this case, it isn't. The only reason we absolutely need to do it is if we would get a minus value in the ln when we substitute the values in, which won't be a problem in this question. In some cases, however, it makes it a whole lot easier. So question 1 that we did at the beginning of the lesson, whole lot easier to e both sides. In this case, probably easier to stick like this. But okay, you've got the option of doing either.
Okay, thank you.
Sorry, 18 is positive, so I don't need the... Yeah, this one, it's definitely easier to leave it in that form. But I can't give you a general rule. I think this is always a good way to go, and it's not impossible. Just this case, actually, it was easier. I'm hoping. Oh, does it say exact value? Oh, it doesn't. Right, if it doesn't say exact value, then we're okay with 3 configs. If I stick with this one here.
Thank you.
So if you'd left it in logs, then you end up with 9/7, 12 ln 9/7. If you did it this way, you would have got the same thing. You've got, well, yes, you would have got the same answer. It just wouldn't have looked quite as nice. It would have been minus ln it would be, yes, you would have got, let me show you, so down here we've got 14 over 18 equals log both sides, multiply both sides by minus 12. And can you see they've done the trick again? They've written that as 12, ln that to the minus 1. So we've got the same answer both ways, but yeah, this way was far more sensible this time, because actually I ended up eating both sides to get it in that form, but then having to log. And because the question didn't say, there's nothing wrong with you having that as a decimal value, whatever the decimal value of that would be. Now this is hard. You know, I say again, particularly the log gymnastics that we go through. You know, it's not fun. If you're not asked to give the answer in a particular form, it's a little bit easier. So I've only done that because I've checked the answer. I probably, if it hadn't checked the answer, I would have just typed that in my calculator and rounded it to 3 significant figures, which is a little bit easier, and similarly I could have done it that way there.
We're going to move on.
We're going to move on, and we're going to just spend a lesson or so just reminding ourselves of the other main application of integration. So we've looked at integration to solve differential equations, which generally are equations which relate to the rate at which things are changing. But the other is to find area. And we're just going to look at 3 examples of integration to find area, which is perhaps, or areas, which are not straightforward. Probably get through 2 today and 1 tomorrow. And then that's integration done. Okay, scenario 1, areas above and below the x-axis. This function here is the graph of x sine x. If I integrated that between a and c, I would not get the blue area, because the area here will turn out as negative, so it would cancel out the area there. So what I have to do is do this as 2 separate integrations. One between A and B, which I know will be positive, and one between B and C, which I know will be negative, but I just ignore the sign. And this question starts off by getting us to work out what A, B and C are. So Isabel, what do I know is true about the graph where it crosses the x-axis, or rather those points?
Y equals 0.
Y equals 0. So we're going to firstly ask, before we do any sort of integration, when does x sine x equal 0? When we deal with quadratics, and we ask a similar sort of question, we factorise them. There you go, I factorised it. So all I need to do is ask, when will that equal 0, and when will that equal 0? Well, I'll do half. And actually, asking when does that equal 0 That's not too tricky either, is it? Go on, see if you can write down. I found A. Can you write down what B and C are? Making sure you remember that in any question that involves integration with trig, we must be in radians. So B and C, I expect to be radians. So okay, Grace, where's the, we already know, I mean sin x is 0 at 0, but we already knew about that one. Where's the next place that sin x is 0 in radians? Pi radians. So B must be pi. And then the last place, Erin? Two pi. Just be 2 pi. Yeah. 180 and 360, but in radians, pi and 2 pi. And the fact it said write down, that's always a suggestion that it should be quite straightforward. We shouldn't be doing all sorts of gymnastics like perhaps in that last question. Okay, that's good news. Right, next thing we need to do is we need to do 2 integrations. However, the good news is it's the same function, so we haven't actually got to do 2 integrations at all. But we've got to do 2 calculations. We're going to work out the area between 0 and pi, and the area between pi and 2 pi. What do you reckon, Lily? How am I going to integrate x sine x? What sort of expression is that? It's a product, so we're going to use the windows, that's right, the weird square, as he calls it, which is integration by parts, which we find on page 7 of the formula book. Yeah, so this is an integration by parts question, where we know that, unlike the product rule, where we put one thing here, we call it u, and one thing here, we call it v, with integration by parts, we put one thing here and one thing here. This thing we differentiate, and this thing we integrate. It nearly always makes sense to put x there, because when you differentiate it, you get 1. See if you can, and we did actually do one very similar to this the other day in a different context. So see if you can integrate that using integration by parts, which is on page 7 of the formula book. This is u, this is dv by dx. We integrate that to get v, we differentiate that to get du by dx. We plug it into the formula halfway down page 7, integration by parts formula. So because I had a minus cos x, I just pulled that minus out to make a plus. Didn't have to do that, you would have got the same answer. So when I integrate this, I get minus x cos x plus sine x. And of course that's the same for both cases. So I'm just going to substitute my values in, and of course you're substituting pi in both cases, so actually you only need to substitute things in 3 times. Make sure you're in radians, and just get your calculator to do the hard work. 0 arrow x, type that in, equals, go back up, change the 0 to pi. So I'm expecting the answer to this to be negative, but I'm going to ignore the whole negative thing. So I get pi for the first area, no units with these sorts of questions, and then this is minus 3 pi, but I ignore the minus, so actually my total area is 4 pi. Areas above and below the axes are have to be calculated negatively, and we need to make sure that we are we're careful when we come to checking our answer with the button on the calculator. So you may remember we've got this great button on the calculator that will work out integration for us. Not allowed to use it to solve problems in the way that we can use it to solve quadratics, but I go to math, arrow is there. So if I type in the problem as it is in its entirety, so it's x sine x between 0 and 2 pi, this is not going to give me the correct answer, because it just does pi take away 3 pi, which is minus 2 pi. It's not clever enough to deal with that. However, if I do it as 2 separate integrations, so I do it from 0 to pi, that gives me my answer, pi, and then I do it from 0 from pi to 2 pi, and change the sign. So you can still use it to check, but it's not clever enough to work it all out in one go. Scenario 1, areas above and below the curve. Nothing new, but there we go. Scenario 2, areas between curves. So this is on page 316, but we're actually going to squeeze this question down and do a part of it. We're going to work out area R1. Okay? We're going to work out area R1. And I'm going to cheat for speed and tell you what the intersection points are. The first thing we're asked to do is define those intersection points by just asking when does one curve equal another, but you get minus pi over 3 and pi over 3. So I'm just interested in working out that area there. And I'll tell you how I always would have done this. I always would have worked out the area under the big curve and then taken away the area under the lower curve. So I would have done it by the upper curve, that's that. So I would have worked out 2 cos x plus 2 between minus pi over 3 and pi over 3. And then I would have taken away minus 2 cos x plus 4, the integral of minus 2 cos x plus 4 between the same points. And that would have given me the correct answer. And that's always the way I did it. And you can do it that way. Absolutely fail-safe. But there is a shortcut. There is a shortcut. And because I'm dealing with particularly gifted mathematicians, I know that you'll spot the shortcut that you can take and ask, why didn't he show me that? The shortcut is that I can do the take away bit before I integrate. So I can actually work out the area between the two curves by firstly saying, right, what's that? Take away that. And when I get that answer, I just integrate it between the two values. So I can do it as one integration. This only works when everything is above the x-axis. Doesn't work if you've got something above and below the x-axis. But I can do that. I can do the subtraction before I integrate, which is a little bit quicker. All right? Now, I've always resisted doing this because I think this step could go wrong, and you then have that would follow through. So the two separate integrations will always work, but yeah, I can't deny that this does work. So go on, just see if you can do that function, take away that function. Just be careful. Take away all of that. See what you get, and integrate it between minus pi over 3 and pi over 3. I'm going to shut up for a while. And we're only doing R1. Okay, just R1. R2 would be the same process. The functions are the other way around because it's anyway, very good. doing a full question, just area R1. Now, I do remember doing this before. When you use your calculator, it gives you a horrible decimal number. So I would just do the minus 2x manually. So 2 lots of pi over 3 is, and just get my calculator to work out 4 sine x. And similarly here, minus 2 lots of that would be plus. And I'll just get my calculator, because we're asked to find it in this form here. So if you type that in on your calculator, as we always do, in this case it doesn't work, so I'm just going to use my calculator to do that bit. So just to be clear, we get 4 cos x because it's 2 cos minus minus 2, and minus 2 because it's 2 minus 4. Coefficients pass through unchanged. Cos becomes sine. Minus 2 becomes minus 2x. So that gives us that. Yeah, calculator's not much help in this one, which is unusual. Normally it's quite nice. I don't know why it doesn't give surds, but because we're asked to give it in surd form, I've got 2 lots of root 3 minus minus 2, so I've got 4 lots of root 3, and I've got 2/3, take away another 2/3, so that's taking away 4/3. And there we go, scenario 2, area between curves, which can be done as 2 separate integrations. We get the same answer if we'd done it my old way, but you can do it as bigger area, take away smaller area before you integrate. Just be careful if you do that, that you get it the right way around. So that leaves scenario 3 for tomorrow, which is the last integration question we will do in lessons. We're then moving on to a thing called numerical methods, which is easy peasy by comparison to what we've done this week. And we're ahead of schedule because I wanted to finish integration this week, so we're sort of 2/3 of a lesson ahead of schedule. Just a reminder that we've done nowhere near enough practice of the differential equation thing, so please try some of those. See you tomorrow.